today to hear better.
Okay, so good afternoon. Thank you for choosing my track. My name is Zbigniew Bodek, and I work in semi-health in Kraków, Poland. And today I will talk about one of our recently completed projects, which is the transparent Superpages support for FreeBSD on ARM architecture. So let's take a look at the presentation outline. I would like to start with the overview of the virtual memory system. For those who are not familiar with the concept, I hope this will enclose the basic principles of operation, and then we'll move to drawbacks and limitations of this technique. Hopefully, this will lead us to the introduction to Superpages. And here I would like to say a few words about the basic concepts related to the generic layer of the Superpages that is implemented in the FreeBSD. And then I will move to the implementation that we've made for ARM v6 and v7 architecture. The last significant point in this presentation would be the validation and benchmarking. Here I will tell you what tools we use to validate our functionality and what results we achieved with and without Superpages. Of course, a few words about future work and what we would like to implement in this area will be provided at the end. So maybe let's move to the virtual memory. Well, CPU cores use virtual addresses to define a particular location in the main memory. So the addressing space that is visible from the application point of view that is running on the CPU core is called a virtual address space. But on the other hand, we have a physical real address space which can contain main memory, memory map registers, PCI, and so on. In addition, we have also, every computer system has its memory hierarchy. So we have small and very fast memories that are placed close to the CPU, like CPU registers and caches. Then we have, of course, main memory. And at the end, we have external storages like SSD disks or some network storages and so on. And each node in that hierarchy has a significantly bigger capacity, lower price per storage unit, but also much longer access time. So in fact, each level in the hierarchy is a cache for a subsequent level in this set. For the CPU core to access any of the data and text, it needs to be placed in the main memory. So the virtual memory system is responsible for choosing which parts of the data or the program will be resident in the main memory at any time. And it is also responsible for dividing the spaces between the processes that can simultaneously run in the system. And so the virtual memory is actually an additional layer of interaction between the virtual address space and physical address space. And it requires also some sort of support from the hardware side. And so actually all the application processors incorporate a memory management unit, a hardware unit that provides translations between virtual address world and physical address world. On ARM, access to memory is shown on the picture on the slide. So the CPU invokes a virtual address that is then translated by the MMU to to the physical frame in the memory. To speed up this process, the MMU incorporates an array of recently used translations, so that if the translation the translation is done with granulation to page. The page is the smallest translation unit, and it's a piece of virtual address space, and is directly mapped to a single physical frame in the physical memory of the same size. So if the virtual address that is used by the CPU is resident, if the mapping for the invoked virtual address is resident in the TLB, we have immediate access to the memory. On ARM CPUs, it's about 0.5 to 1 cycle overhead for TLB hit access. And ARM processors have their TLB hardware managed. It means that we don't have really access to the contents of the TLB, and the contents are filled and evicted according to the algorithms that are implemented in the hardware. So on the other case, when the translation for the particular page is not resident in the TLB, we've got so-called TLB miss that needs to be served by the memory management unit. And so the MMU performs so-called translation table walk that will try to find the appropriate entry in the translation tables that are resident in main memory, and put it into the TLB so that a subsequent access to that address will succeed. Of course, the search is not linear, so this is not exactly the walk through the tables, but bits from the virtual address are used to index the translation tables. However, if the entry is not found, we've got the exception that needs to be handled by the operating system, and involves creating a new entry in the page tables. So we can see two possible drawbacks in that architecture. First of all, the TLBs are usually quite small. This is motivated by the fact that we want our TLBs to be very fast, and on ARM especially, we want them to be energy efficient. So in that case, bigger TLB would mean more logic, and that would mean bigger power consumption, and eventually may also cause lower speed in terms of searching through the TLB. Usually, contemporary processor architectures support more than one page size. On ARM, there are 4 page sizes when using a short descriptor format. It means that when we are not using large physical address extension, and these are 4 kilobyte pages, 64 kilobyte pages, 1 megabyte pages, and 60 megabyte pages. But usually we want to use 4 kilobyte pages, so the smallest allocation unit, because we want to keep the low fragmentation factor, and so we want the memory to be utilized in an optimal way. In addition, on ARM, every TLB miss involves 2 memory accesses, 2 accesses to the main memory. First access is done to L1 table that you can see on the left side, and the second access is done to the L2 table on the right side. L1 table serves as a page directory in that case, and each entry in L1 table points to the L2 table. So L2 table includes 256 entries that map 4 kilobytes each, and the blocks in the middle are not related to the way that hardware sees the structures in the memory, but it's the way how FreeBSD PMAP handles those structures internally. So apart from TLB-MIS overhead itself, we have two memory accesses on each TLB-MIS. Summarizing this, we have the limitations related to small TLBs and to 4 kilobyte page sizes that we want to maintain dense granulation, and so the small fragmentation factor. And due to that, we have a small TLB coverage. TLB coverage is a factor that describes how much memory can processor access at any time without TLB-MIS. And in our case, it would be like 256 kilobytes with TLB of size 64, which is very common in ARM world. So of course, we cannot enlarge the TLB itself, but we could use bigger page sizes, but this would bring us worse granularity and enlarge our fragmentation. And also we could let the user decide what page size he wants to use for his application, but this kind of contradicts the idea of virtual memory as a transparent layer for the user. So here comes the Superpages technique that overcomes this issue by adjusting mapping size to the actual system needs at that time. This mechanism is well elaborated mechanism in the FreeBSD. It works on 32-bit Intel architecture and AMD 64. And well, it's divided into two main parts. The first part is a thinking part, and it's responsible for managing a machine-independent part of the Superpages support. And the second part is related to, you may say, doing stuff in PMAP. So the Superpages is based on reservation-based allocation, and it's strictly related to the need that if we want to use several page sizes, we need to take into consideration that the area covered by a superpage will need to be continuous in both virtual and physical address space, because the size of the superpage will cover the exactly same size in the physical frames. So the VM, when virtual objects is going to be placed in the memory, the VM reserves an area that is at least superpage size or bigger. And according to the rules of paging on demand, we allocate the pages inside that reservation, and if we populate the reservation map, we have a candidate for promotion to a superpage. Of course, if the process that obtained the reservation is not populating it, we would waste the space. So if we have a lazy process that is not utilizing its reservation, it can be evicted by another process that is actively using the memory. So as you can see, this mechanism truly adapts to the actual system needs, so that only active processes that are actively utilizing their memory will have their pages, will have their mappings promoted to the superpage. Between the machine-independent layer and machine-dependent layer, we have a very simple interface. We need to create two definitions. The first definition informs about how many superpages we will have in the system. And the second definition provides the information on how many pages from the previous level of reservation will create a superpage in this level of reservation. So in our case, we have only one reservation level, and our superpage will consist of 256 base pages from the previous level, so the level 0 order will be 8. And so our implementation introduced PMAP extensions that provided promotion routines, demotion routines, page creation, removal, and shared mappings management. And of course, we needed to add some other modifications to the PMAP module so that all of this would play together and work. Let's start with the page creation, which is super page creation. We can create a super page in two ways. First of all, we can put super page mapping directly if we know that the virtual object that we want to map is at least super page size, and we received appropriate information from VM in the form of message that the reservation is fully populated. We can just insert the mapping using insert the mapping directly and map it as read-only. But in normal circumstances, we rather use a promotion mechanism, which involves a couple of checks in the process. First of all, we need to find out that our reservation is fully populated, and in both cases from VM and in our PMAP structure. So we check the L2 bucket occupancy, and if it's full, it means that 1 megabyte virtual chunk is fully mapped. Apart from that, we need to check that this mapping is continuous in the physical address space, since we know that it is continuous in virtual address space because this is how it is organized in the PMAP in the memory. But we still need to check out the physical alignment and physical continuity. So we actually need to check each of the page table entries for their physical address and if they are correct. We also need to check all the attributes and access permissions of the base pages within the newly created superpage. They have to be identical because after promotion we will have only 1 bit per whole area to determine the page attributes, flags, and access permissions. So if all of this is correct and the reservation is fully populated, we can promote the page to a super page. Summarizing this, we create a super page in two ways: by a direct mapping from PMAP enter object, or by promoting base pages to a super page. And also we prefer read-only mapping, since we have only 1 bit for a super page that will determine if the page is dirty or it hasn't been written. So it is better to promote a page as read-only, even if the base pages are permitted to be written. It's better to change the attributes to read-only and promote the superpage read-only. This is motivated by the fact that if we promote a superpage read-write, we will need to page out the whole area under superpage in case of paging any of the base page within. So since we have only one bit for entire superpage. And there is a way to map a superpage as read-write, and it is only when all the pages within the superpage are already written. Okay, so we need to check continuity in physical and virtual address spaces and page attributes. And also during promotion, we are trying to preserve the old L2 table for future use, especially when we want to demote the page. We need it to be, we need to do it fast, and we need to recreate L2 table so that it won't result in further faults on the addresses. And also, if there is only an attribute change, we can re-promote that page fast. Also, we used a single PV entry for a superpage. PV entries are used to track shared mappings along the PMAP, and for a superpage we use one PV entry for the entire area, and all PV entries from the base pages can be freed at that time, so we need to allocate them again if we demote the page. During superpage removal, during superpage demotion, we recall the old L2 table or recreate it if there is none. Of course, this might not succeed, so then we will remove the superpage and we need to recreate the PV entries. And we demote superpage when we want to change attributes of the base pages within, or we need to page out one of the base pages or all of the base pages within, or we try to write to a read-only superpage, and this is the case that I was talking about earlier when we map superpage read-only. So, summarizing this, we created a support for 2 page sizes. We have a 1 megabyte section that serves as a superpage, and 4 kilobyte small page that serves as a base page. So we've got one TLB entry that maps equivalent to 256 base pages, and shorter translation table if it goes through only level 1 translation table.
Quick question: is the superpage size configurable, or is it?
No.
It's always going to be
Yes.
1 megabyte.
Yes.
Picture?
Yes. If all of this is yes. Well, we used 1 megabyte page size because it is natural that we wouldn't need to modify L2 table entries. We just drop them for a moment, and we use 1 megabyte page size to map the whole megabyte area, and therefore we don't need to perform a second memory access to L2 table. So in theory, this should be faster than going through 2 levels of tables and mapping 64 kilobytes. Also, since the 32-bit Intel uses 2 megabyte pages, this was similar size, so it was good for comparison of the results. Okay, so if all of this was clear, then I hope we can move to validation and benchmarking. Right. So we used several benchmarks to test our implementation. The best or most noticeable results were gained using giga updates per second benchmark that performs random memory accesses. And also we used LM-Bench suite that incorporates stream benchmark for memory bandwidth benchmarking. Of course, self-hosted word build is a good test for everything, so we tried that too. And fork bump and stress2 utilities were used as a sanity checks to check how will Superpages support manage in a stressed environment. And recently I tried to use some hardware performance counters to get some more detailed information about TLB misses and how many cycles do we waste for a single TLB miss, and how many cycles do we waste on the two-level TLB miss. Translation table walk as a result of TLB miss. And as a test platform, I used Marvell Armada XP, which is a quad-core ARM v7 processor. And here we see the results. In the first row, we've got results from the giga updates per second. The CPU time using Superpages, that was the CPU time that was used during the test, dropped by about 30%. And in this shorter time, we gained about 30% more updates per second. LM-Bench, or should I say stream, gave some less significant results, and this is probably because it is using floating point arithmetic in its tests, but we've got quite good random memory latency, which dropped by almost 38% using Superpages. And self-hosted build world, in self-hosted build world we've got over 1 hour improvement using GCC and no influence using Clang. Regarding hardware performance counters, then I used per CPU TLB miss counter and per CPU cycles counter, and my goals was to measure, or should I say estimate, TLB miss penalty and check the TLB miss reduction caused by Superpage on various tests. And the test was was performed on a memory area of size twice as much as TLB size multiplied by Superpage size. I configured the PMU counters to be accessible from user land, so that my user application could configure the counters and read the values. This can be done only from the supervisor mode, so you can do this from using mini kernel driver or kernel module. And I configured the PMU counters to catch appropriate event. In my case, only TLB miss was relevant, since my CPU has a dedicated cycles counter. And the test was performed as displayed on the screen. First I allocated the memory, then I touched all the 4 kilobyte pages within that area. Effectively, when Superpages were enabled, I created Superpages in the process. Then I enabled PMU counters and touched 64 pages with 1 megabyte interval in the area from 0 to 64 multiplied by Superpage size, and disable PMU counters. So effectively, I've got TLB miss in both cases with 4 kilobyte pages and 1 megabyte pages, but in 1 megabyte pages I should have get a shorter translation table walk. So using this data and a simple formula that involved also checking how many cycles take a row loop of iteration for the test without TLB miss, I was able to account how many CPU cycles are wasted for a single TLB miss. And when Superpages are enabled, we saved almost 100 CPU cycles per TLB miss. And on the second test, I tried to make 256 iterations through 64 megabyte area, so that TLB thrashing will has a significant influence, and we can see that more or less the results are as expected. In case when Superpages are enabled, we see very little TLB misses, since after the promotion we basically keep the area in the TLB, and there are no additional TLB misses. But in case of Superpages disabled, we can see that there is a quite significant amount of TLB misses, since we are thrashing a TLB on every loop. So regarding the future work, then we would like to support 64 kilobyte pages eventually. This is because more applications will be able to use to take advantage of the Superpage, because not all normal applications are so memory hungry to utilize over 1 megabyte. And this will also make the promotion more incremental, so we'll probably see different behavior when using few Superpage sizes. We also want to enable Superpages by default, as it is done on the Intel platforms, because now it is disabled by default, and one needs to enable this in PMAP code or by tunable variable from the loader. And also we would like to move all status flags from PV entries to page table entries, because on ARM we store a wired indication and permission to write in PV entries, and this involves additional searching on promotion attempt. So if we enable type extension on ARM on FreeBSD, then we will be able to put those 2 bits in a spare bits that will appear in page table entry, and we will have less overhead on promotion failure, but also overall faster page management on ARM. So if you are curious about this project, there is a wiki page, but probably the more detailed information are in the paper that you received during this conference. But of course there is a project's wiki page, and you can visit it. And I would like to thank the following people that were involved in the project, especially Grzegorz Bernacki and Alan Cox for their great help during this project, and to project mentors and sponsors Rafał Jaworowski and Bartłomiej Sienka from SemiHealth, and of course great thanks to the FreeBSD Foundation who sponsored this project. As I can see, we have about 10 minutes. Yes?
Why are they off by default?
Because when we integrated this code to the FreeBSD, we didn't know how is with the stability we tested it in Semichov, but the tests were very local in our lab, right? So we wanted the community to test this first, and I don't know how the tests were, but since this was upstreamed, I'm running various tests at our lab, and I've made some improvements to this implementation, and at this point I consider it stable, so I'm slowly going to change this back to to enable by default.
Two questions. One is, you used PMC directly, the counters.
Yes.
Do you have code that would add them to the HWPMC libraries and HWPMC drivers? Or is everything just, is it assembly language and checking? Does it mean have to do the PMC work, any PMC work for ARMS?
No, this was done by me recently to get the data for the conference to show you the influence of the Superpages. So this is actually in my assembly entered to the kernel module and in my assembly. Battery state name.
The other question I had is
Now Superpages are enabled, and we did do the same test. And as you can see, we have a significant reduction of the cycles per TLB miss, and TLB miss is recorded. So, okay, so this will be all from my side. So thank you very much for your patience and for your attention. So if there are no questions, then thank you.